Next up, we have our middle school science teachers. And I welcome Larry, Berkeley, and Jesse, and they will share a little bit about themselves and then jump on into what middle school science is like at Catlin Gable. So welcome, I'm gonna turn it over to you three.
Thank you, Ted. Excellent.
Okay. Hi, everybody. I'm Larry. I teach sixth grade science. Hometown from California, but my dad was Air Force, so really everywhere was hometown. I went to Cal Poly for my bachelor's and University of Florida for my master's. And I've been here at Catlin since 1998. I used to teach in Eastern Oregon in public school. And before that, outdoor school education in California. I was a contract field biologist for numerous agencies, and a really cool job was Peace Corps. I was a Peace Corps volunteer in Jamaica and worked at a zoo. That's where I discovered teaching. That's what put me on the path to be a teacher. And I was a ranch hand. That put me on the path to not be a cowboy. My wife is an ELL teacher for Beaverton School District. And I have two daughters, both went through Catlin, and they're both now in graduate school. My passions are gardening, hiking, camping, travel, and searching for mushrooms and living to tell the tale of those mushrooms. So I'm very, very happy to be at Catlin Gable, and I really look forward to teaching your sixth graders.
And hi there all, my name is Jesse Lowe's. I'm a seventh grade science teacher, and it's nice to see you. I can't see you myself, but I know you're out there and appreciate you all taking the time to come visit us. And just a little quick introduction to myself. I'm originally from Vermont. I went to school in Colorado at Colorado College and studied biology there, and thought I was going to be heading off to do field research and furthering the degree in ecology and other biological fields like that, but it felt pretty hard for teaching, kind of bouncing around in a handful of different capacities, working at an outdoor school in California, actually teaching English in South Korea, leading wilderness trips for kids, and then fell in love really, really, really hard at working at OMSI as an outreach educator, where I drove all over the Western US and even managed to make it up to Alaska to deliver hands-on science programming in the form of assemblies and classroom programs for kids, and just decided that's what I wanted to do, and I went and got my master's degree at Lewis and Clark here in Portland, and after a little bit of work elsewhere, I landed at Catlin, and this is the beginning of my 9th year. So it's exciting, and I love it, and we get to do all sorts of wonderful things with kids and engage them creatively in the world around them. My world that I'm not at Catlin involves my wife. I have a 7-year-old daughter, a 3-year-old son, and a brand new puppy, Poppy, which you may hear barking. We'll see. Hopefully not. Passions of mine are largely outdoor focused. So climbing mountains, trail running is a recent love of mine. Bikes, a funny form of skiing called telemark skiing, where your heels aren't connected. And yeah, backpacking, reading, just being outdoors. And I love doing it with kids. So that's me, Jesse, 7th grade science.
Hi, my name's Berkeley Gadba. I teach 8th grade science. Just to tell you a little bit about myself, I grew up most of my life, my childhood anyway, overseas. I was born in Norway and lived in Eugene for a little while before heading to Dhaka, Bangladesh. And most of my childhood was spent in a city called Kobe in Japan. I came back to the United States to go to college. I was in California at Stanford, and then went to the University of Washington to get my master's in teaching. I have taught all over. I taught in Seattle, Washington, in Chapel Hill in North Carolina for 4 years, and then in Beaverton, locally here in the Portland area until about 4 years ago. And 4 years ago, I made the change to come to Catlin. Like Jesse and Larry, I love teaching middle school, and I'm just very excited to be at a school like Catlin. And this is a photo of I have 2 daughters and a husband named Matt, and we've lived in the Portland area probably about 15 years now. And a few of the things I do outside of the classroom, I love to run marathons, half marathons, 5Ks. My family loves to travel. And then I love to eat all kinds of food and cook. So very excited to be here with you this evening. I have the pleasure, I get to talk a little bit about our sort of philosophy and what guides our work as a middle school science department. And so 4 years ago when I arrived at Catlin, our middle school science department, in conjunction with the lower school and upper school, started adopting and using the next generation science standards. And these standards are really about kids doing and experiencing the work of scientists. So I want to spend a little bit of time talking about that. And there's sort of 3 major strands that are part of the next generation science standards. And those are the science and engineering practices, the disciplinary core ideas, and the cross-cutting concepts. And these really help guide our work so that kids have a more cohesive experience throughout their schooling. And in particular, Jesse and Larry and I work for that cohesion over the 6th, 7th, and 8th grade years at Catlin. So the science and engineering practices of NGSS, there are 8 of them. And I sort of like to view these are what scientists are doing. So no matter the topic that we're studying, we're asking questions, we're using models, we might be analyzing data, communicating information, or conducting investigations. And so, for example, if I'm teaching a unit on human impact in the environment, we might analyze some data and then argue from evidence to support our ideas. Similarly, as an example, in the chemistry and chemical reactions that I teach, we might use modeling because atoms and molecules are too small for us to see. We might use models to help us better understand the observable that we have in front of us. We might use models to model the unobservable pieces that we can't see. And then the cross-cutting concepts, there are 7 of those. And one way of thinking about the cross-cutting concepts are, they're sort of a lens through which to, again, view all topics within science. So it's also a way for teachers to sort of ask questions and to allow students to explore the connections across topics. So if I'm teaching a unit on genetics, we might look for patterns in inheritance across different species, or at the Jesse might be teaching patterns in weather and cause and effect. What's causing those patterns? Why do we see that? And so these cross-cutting concepts sort of help students to see, again, the connections as they go from topic to topic. There's certain ideas that carry over no matter what in all of our topics that we study in science. The 3rd strand is the disciplinary core ideas. And this is maybe the more traditional, like what is the core content that students are going to walk away from? And these are key ideas that build on each other over time. So in 6th grade, we look at cells all the way up to systems within organisms. We have an introduction to chemistry and look at physical changes in matter. And then Larry also teaches about the Earth, Moon, and Sun systems and our place in the universe. In 7th grade, Jesse, in terms of big disciplinary core ideas, talks about ecosystems, forces in motion, energy, a little bit on waves and electromagnetic radiation, and our Earth's systems. And then as an 8th grade science teacher, I teach about heredity and genetics. I have a unit on natural selection and evolution over time, an introductory unit on chemistry and chemical reactions, a little bit on sound waves, and then all 3 of us incorporate engineering into our work as well. And if we were to sort of look at the trajectory of this for a 6th, 7th, and 8th grader. This is maybe how a student would experience 6th, 7th, and 8th grade at Catlin. And I just wanted to point out that as we're looking at this experience, it's a very integrated curriculum or integrated approach. So rather than teaching life science one year, earth science one year, and physical science another year, all of their years, they get a little bit of all of those science disciplines.
Okay. So in 6th grade, one of the engineering and inquiry activities that I do, or we do, is how can you crush a can with air pressure? And that's my second unit. And one of the benefits, which is putting it mildly, I guess, of remote learning is normally I do this in the class. So last spring, I videotaped the activity and challenged the students to do it at home. They weren't required to do it, but most of them could do it. And so now if we can play this video with lots of power and pressure. So let me try one more. I'm going to take this little one here, put it upside down. And once it's in the water, I can pick it up with my bare hand. Okay, this one. So your job is to figure out, why did the can collapse? It wasn't my hand. So I took an empty soda pop can, put in a little bit of water, and then put the can upside down here, and it collapsed. So I went from a can like this to a can like that. How did that happen? Okay. And so the benefit of that video was that students could watch it over and over ad nauseum as long as they wanted to get the information they needed. And then we had a question, well, how big? We have this can behind my room, this steel drum. And I posed the question, what would happen if we did the same thing with a steel drum? And very few students thought anything would happen. So I sealed the top, drilled another hole that a cork would fit in it, and then I put it on a burner in my yard. And we had steam coming out. And this too is on video, but it's way too long for this presentation. And corked it after the steam was coming out, treated it just like the aluminum can, and the kids got to see it crunch. And it was pretty dramatic. And this actually can tie into industry, because the students found on their own, without my prompting, they found that a railroad tank car imploded on purpose. So the railroad people intentionally made the tank car crush with atmospheric pressure. And we had to figure out, why in the world would they spend $200,000 to do that? And apparently just in cleaning a tank car without properly opening the vents, they can crush that car just with atmospheric pressure and steam. So that's just one example of the engineering kind of things that we do in 6th grade science.
This is Jesse again, and I'm excited to share with you a project that I've been working on with students. I guess it would be going into its 8th year right now, and it's something that gets me excited, it gets kids excited. It really ties into the experiential work that we strive to connect kids to at Catlin, and it's a field research project in the Coast Range at a place called Hyla Woods. I developed a partnership with a forester in the Coast Range over by Tillamook, and he or towards Tillamook, and he was really interested in trying to get a better understanding of the quality of the water running through his forest that he was managing. And for I guess 8 years, students and I have been going to his land, and we've set up 12 field sites and collected a whole assortment of data to understand kind of ecosystem dynamics and health, for everything from dissolved oxygen and temperature to looking specifically at the bioindicators of macroinvertebrates, or the organisms living in the creek that are either tolerant or sensitive to various degrees of purity or water degradation. So this is a really engaging unit. Kids are in the field. They go 2 times spread over a period of a month. And we bring in all sorts of threads that are connected to the Pacific Northwest, talking about land usage, salmon, conservation, kind of how decisions make an impact on the land, both historically and in the present, and then moving into the future. So if we go maybe the next slide, there's a little shot of where this is. I get kids to think about space, not just on a map in the Google map way, but as watershed. And so looking specifically at the Nehalem watershed in this case. And then I guess the final image is just a collection of kind of the quiet, contemplative scenes that we get there. So it's rambunctious and it's wild getting all this data, and then it's also calm and centering too. So it's a real joy of mine to get to bring students and share something like this with them in a real meaningful way. Our data is published by the landowner on their website. Students write up annual State of the Creek reports. It's an engaging project, and it's one that we can't quite replicate remotely, but I'm working on doing it in another form and looking forward to coming back and doing this with our muddy boots in the water. So, and I should point out that Berkeley has other great examples, but I know our time is limited, so we had to draw straws for who was introducing NGSS and who was sharing some units.
Thank you.
I think we're question time now, I think.
I think so too.
And I wasn't sure, Mary, are you fielding the questions for us, or do we?
I am happy to field the questions for you if you would like me to.
Cool. Is it just,
I can do it.
Oh, cool. Great.
Yeah. All right. How do you enable science experiments remotely? Does the syllabus look different as a result?
I can jump in on that one because I mean, it is frustrating to try to carry out science remotely. Just it's a puzzle, but it's also a kind of a wonderful puzzle if you look at it in the right way. I found myself being thrust into this remote reality as I was shifting gears into a unit all about rocketry and force and motion and everything that I usually do, which is really designed around teams, like students acting like engineering teams working on modeling rockets and launching them, and that you just couldn't be done. And so I ended out having to pivot pretty dramatically, and I started doing a bit of an inventory of what I thought students had at home, and developed a lab that I called a very canned lab. And it was reliant upon cans of food, so soup cans, bean cans, which it turns out every student had in some form or another. And it was full cans, empty cans, rolling them down ramps, measuring the distance, like using that as a way of approximating the variables around force and motion and acceleration. So there's a creative piece, you can't necessarily do all the same things, but what's wonderful about NGSS is that it's less about these like particular experiments that you need to do and more about the way in which you weave together these disciplinary core ideas, cross-cutting concepts, and science and engineering practices, which like you can find creative ways to do that with the stuff you have lying around, which is actually kind of a cool challenge.
Yeah, I think that's the secret, is we have to adapt our activities to stuff that's available at home. So there's more lab work in the kitchen. And for example, in my first unit on the solar system, we would use the entire campus to build a scale model of the solar system. And now we use a roll of paper. So things get adapted.
Mm-hmm. And I could piggyback on that as well, as I've started with chemistry this fall, as I would in the classroom. But I've, much like Jesse and Larry, been adjusting with what students have available at home. And although I did send home graduated cylinders and scales to a few students, a lot of the labs are done with food and how we see chemical reactions happening in our everyday lives. In some ways, it's really a cool opportunity for kids to see science in their everyday life more than ever before. So that's really exciting.
Thank you. Mm-hmm. Right. How do you assess students in each of your science classes?
In my class, we have periodic quizzes on concepts, on vocabulary. We have discussions. So a lot of it's informal. Is the student engaged? There's a lot of collaboration. So it's all of those together is in my assessment. I told the teachers earlier, the main thing I'm looking for is engagement. If you're engaged, you're doing all the right stuff. And we just try to give you different ways to show your engagement and show your understanding.
And I would maybe add to that, as a department, we have a rubric that is consistent 6th through 8th grade. And so that's another way that we're assessing students maybe more formally at the end of a certain amount of period. I would add to what Larry said that, formatively in the moment, we're assessing and reading student work and giving them feedback all of the time. But with the rubrics, we rely on, again, the NGSS science and engineering practices, looking at how they're using models, how they're conducting investigations, what kind of questions are they asking, as much as we can.
Chime in and say that an area that we work a lot, or specifically in 7th grade, I'm working a lot with students on, is developing arguments. So claim, evidence, reasoning is something that comes up, interestingly enough, in English classes, and then we see it again, in other classes, but certainly in science, is like, how are you communicating your conclusions, your ideas, and then supporting that with evidence and reasoning. And then I have some different structures that students can use, but then also an assessment rubric for that, as well as other assessment rubrics for specific assignments that deal with other skills, which are frankly harder to assess than just content understanding, which you can get at a little bit more effectively in kind of more of the classic quiz or exam styles. So looking at ways to assess skills and using rubrics and trying to really drill into student understanding is key, and it's tricky, but it's what we aim to do. And I think we're set up for success with it, with the students we have and the support we have, and just having each other collaborating. So
Thank you. All right. In a non-pandemic world, typically what's the balance of students working individually or in groups in science labs and experiments?
I can talk a little bit about that. So I think in all of our classes, students sit in, at tables in groups. And so there is a lot of daily sort of group work that just sort of happens, whether it's in discussions about a topic or sharing of work or reading of each other's papers and things like that. But, and then in our classrooms, we would also have lab stations that students might be paired in partners and have lab partners that they might do an investigation or a lab group with. And then there's always individual time as well. I don't know if you want to add
I agree with that. I'm trying to think of
No.
anything to add, but I think it's a mix. And I think I talk to my students about the fact that we often have this idea in science of this like lone heroic figure who by largely himself, because of the bias of science, but himself, herself, theirselves, discover something. And that more and more and more, almost exclusively now, science is done because people are working hard independently in collaboration. And so really flexing that collaborative skills is super important. Yeah, so it's both individual and all sizes of groups.
Thank you. I'm curious, there's a lot of talk in the news about believing scientists and believing in science. Are there ways that you incorporate sort of just the current events specific to, sort of talking about believing in science in casual or formal ways in your classrooms?
I don't talk about believing in science, but I'm always connecting what we're looking at to what's in the news. So for example, last night and tonight, Mars is incredibly bright, and we lament why Portland has so many clouds, so we can't see. So I'm always offering the kids a perspective, a worldwide perspective or a local perspective on anything that ties into the curriculum. And then that brings up a lot of interesting feedback from the students. So it's just basically looking at evidence And we're always asking why. Why is that happening? Or who can explain this?
Yeah.
I would say also first of all, it's a great question. I mean, I think that we all should be asking that question right now, which is how do we ensure that we as citizens, both older and young, are able to actually determine um, well-established science from pseudoscience or fiction or fear. And the best way that I think that we can do that is this work of decoupling science from simply being a collection of facts that you just take as being true to seeing science as being more of a culture or a vehicle or a lens through which you can understand, navigate, or view the world. And when you start looking at that with students, and you start really looking at the tenets of things like healthy skepticism, or open-mindedness, or like analytical thinking, like it becomes apparent that those tools are more effectively shed light on reality than tools that are like fear, or tools like divisiveness. And so there is no perfect answer to that question, but I think that when we start looking at science less as a collection of facts that you accept and more as a way of actually digging into unclear ground to really get to what's actually going on, I think science presents itself as an effective tool, and kids can tell the difference.
Anything to add to that, Berkeley?
I just think it is a great question. And I think the more we can look at current events and what is happening and say how is science communicated to the public and who is writing that and where is their evidence coming from, and the more we can get students thinking about that and asking that question and examining that, the more we have scientifically literate citizens going out into the world in the next phase of their life. So yeah, I think that it's an important question.
Can I just draw a really quick cross-disciplinary connection now that I see my colleague Elizabeth Ryan in the room, who's 7th grade social studies? She's doing a really cool unit all about looking at logical thinking and the way in which people can try to spread fake information through different fallacies. And so I love it when we find these connections across classes, where in that case we're also looking at how you can tell the difference between like something that's well established versus something that's totally some zany conspiracy theory. So
Awesome. Thank you.
that's the baton pass, I guess. Sorry.
Got 2 more minutes.
Oh no, I'm not trying to get out. I just was.
How would you describe the science homework load that a 6th grader can expect? And I'm guessing this is probably in a non-pandemic world.
Yeah, so typically it's 20 minutes to 30 minutes, like 3 times a week, possibly. So it depends what the project is. Some projects require a little bit more, but most of the time it's no more than 30, and often it's less than 20.
And maybe if Jesse and Berkeley, you want to chime in for your grades, that might be helpful.
I also, just to kind of work from 6th to 7th, I also work on a 30-minute kind of max for nightly homework assignments, and even communicate that with students. So 30 minutes of work looks different for different kids, and there's a level of honor and trust that goes into ensuring that it's 30 minutes of focused work. But if you put in 30 minutes of focused work and you don't finish some nightly assignment, I have kind of a tap out time where kids can write a little note. And it's work that we're going to follow up on class, so they don't miss it, but it just ensures that people aren't doing hours and hours and hours and hours, because we need that time for ourselves too.
And as an 8th grade teacher, I would say the same, 30 minutes with this very similar philosophy as Jesse is describing.
Thank you.
Great. Well, I want to thank our science department. Thank you, Larry, Jesse, and Berkeley. Great presentation and a great way, again, of viewing how they're stoking curiosity in students, as well as, science isn't about content. That's a lot of kind of how Catlin Gable thinks in general. It's not just about content. It's about these skills and engagement and being able to go out in the world and do great things with what you've acquired at Catlin Gable.